Greetings again. This is Rifat Sipahi for part two of the CCTA workshop. And as you will recall, towards the end of part one, we have reached this point, as you see in the slide, to two main tasks, and then identification of the delay parameter space via decomposition. I don't want to really repeat everything from that recording, but just to refresh our memory, with all these discussions up to this slide, we have motivated and explained how we get to this point, where our goal is to identify whether or not system eigenvalues can ever be on the image axis at values s equals j omega. And our goal is to find all the delay values tau and all the values omega for which eigenvalues touch the image axis at s equals j omega. And once we find all those delay values, tau star and omega star, such that the system characteristic equation is zero, our goal is to then identify, starting from zero delay, how these eigenvalues move, in what direction do they cross the image axis, and whether or not they go from left to right or right to left across the image axis, and use that judgment to decompose the delay parameter space into stable and unstable regions. Knowing whether or not the system is stable for zero delay, as an example, when the delay is zero, imagine the system is stable, and knowing that the eigenvalues will cross the image axis for a delay value tau1 star. Imagine that is the smallest positive delay for which the crossing happens at j omega 1 star. We know that stability will be lost once the delay is equal to tau1 star or is slightly larger than that. And knowing that, imagine the next larger delay value for which a crossing happens is tau2 star. And knowing that imagine the crossing is from right to left, then we know that the unstable pole that was created earlier with a smaller delay than tau2 star will actually turn around and cross over to the stable half plane. This may happen to be the case while the remaining all eigenvalues all still remain in the stable region, obviously not shown in the figure. Then it's possible that we may have stable and unstable reverses, what we call, along the delay axis. Now, what I would like to really mention here is that I am really summarizing here from a variety of sources and to bring you a compact presentation. And obviously, I'm not getting into all the details of all the methods I presented or I will present, but I'm trying to give you sufficient background to crack the door open and for your curiosity. So then, obviously, you would need to investigate all those manuscripts very carefully. I'm only summarizing them to the best I can within a couple of slides. And that being said, there are obviously improvements on these tasks and how they can be executed, whether task 1, task 2, or delay decomposition identification. There are some improvements, theoretical, numerical, computational, that one needs to be aware of. But if you step back and look at the approach in a nutshell, these are maybe the three main steps one takes to analyze stability. And of course, if you have not just one delay, tau, but you have another delay, maybe h, another delay, who knows, gamma, right? If you have multiple delays, then the problem becomes extremely complicated. Nevertheless, the approach is still more or less based on three steps, as we demonstrate here. Now, something really interesting here, and again, we saw this problem earlier, and what we found out was that the crossings happen at the value omega equals 10, and for these delay values, pi over 2 plus minus 2 pi L divided by omega, and omega is 10. And something that was actually convenient in this example, which I didn't highlight earlier, is that the exponential function here appears only once, and therefore the Euler form can be used to solve or isolate the omega solution very easily in this problem. This is the way it is set up to demonstrate the main idea. And nevertheless, if, for example, you have another problem where the characteristic equation has another delay term with commensurate degree 2, let's make this maybe 7, sorry, and minus 2 tau s is equal to 0. In such cases, the commensurate degree becomes 2 because that's the largest integer value that multiplies the baseline delay value tau. And in this case, if you could still write this equation with Euler identity, but then you will end up having a cosine term 2 tau omega in the equation due to this 2 here. You will have also a sine 2 tau omega term due to this term. So then you will end up having a cosine tau omega, sine tau omega, a cosine 2 tau omega, and sine 2 tau omega terms in the equation. Then it will be very likely not easy to analytically isolate omega from that equation because of multiple sine and cosine terms with different arguments. And so that is, you can see how quickly this approach could fail or could fall short when you have multiple commensurate degrees. And one may wonder, why would one have a commensurate degree 2 or 3 or 4? It depends how complex your control problem is, how many multi degrees of freedom you have, and how many actuators you have, and how many of these actuators or sensors are subject to time delays. But if you remember the state space representation that we have shown for retarded type systems, ax star equals ax plus b xt minus tau, clearly these exponential functions come from the Laplace transform of the delayed state. And if the rank of b is larger than 1, you will end up having commensurate degrees. So rank of b is actually the degree of commensuracy, degree of commensuracy in the system. So if the rank b is 2, then you will have an exponential minus 2 tau s as well as exponential minus tau s in the equation. All right, so let's just move on. And we already solved this problem. And what we found out is that at s equals j omega, omega is 10, we find that the sensitivity is positive. And what does that mean? That means that the crossings are from left to right, and there are no crossing from right to left. And therefore, we can summarize what we have found out as follows. When the delay is 0, we have a stable system. We know that. And so we have the complex plane, real and imaginary. And our stable pole was at, let's take a look and remember, it's at minus 10, right? Okay, so we have a stable pole at minus 10. And then imagine we start increasing the delay value, tau equals 0 plus. We will still be stable. Why? Because we have a retarded system. Stability property will be preserved from 0 to 0 plus delay. And eventually, at some point, when delay becomes sufficiently large, right, and we know that value, pi over 20, when delay is pi over 20, we know that we'll have a pair of poles on the image axis at j times 10 and minus 10j. And we also found out that their crossing duration is positive. And therefore, as the delay is increased to pi over 20 plus a very small value epsilon, these poles will go to the right-hand side. Of course, in the meanwhile, the pole at minus 10 will be moving, and we need to check in what direction it moves. So I don't know right now, but we can do another sensitivity analysis to investigate how this pole will be moving. Maybe it will be moving towards right, maybe it will be moving towards left, and that's something we have to investigate. So obviously it will not be there stagnant. As the delay value changes, it will also move. And what is critical is, from stability point of view, there will be a pole crossing across the measure axis at 10j. And as the delay value is increased further, right, based on this rule, right, the next delay value for which the same crossing will happen at 10j is going to be pi over 2 plus 2 pi divided by 10. Okay, So that's 5 pi over 20, so pi over 4. All right. In other words, now is we hit the delay value further, and if you hit the critical value pi over 4, we have another pole that was probably somewhere over here that will actually come over and then cross over the same crossing point. And likewise, as the counter L changes, right, from 0, 1, 2, 3, for different delay values tau L, as we change the delay values, there will be other poles coming and crossing over this 10J value infinitely many times, because there are infinite delays that will make this crossing possible. And we know that all of these are from left to right, because that's what the calculation, right? If you go back, right, we know that all these crossing are from left to right, because as the calculation is in this form, right? It's always positive for any delay value. Again, here, this property that I encircled here holds, and for this very particular problem. And then one may wonder, well, if you have maybe other commensurate degrees, right? If you have a general form characteristic equation, right? If you have a state space, if the rank B is not 1 and something larger, what properties can we expect? Would we expect similar properties? And those are some questions the literature actually has answers for, and I haven't answered them yet in my presentation. But I thought I would just do a quick recap here before we really go to the second step. Second phase of the presentation. Okay, so keeping those in mind, this is now the understanding. Now, since we are already discussing this example, right, and maybe let's go away from this example, right, and let's remember that a theoretical problem that we were actually discussing earlier, right, it is very likely that one may have two crossings. Maybe, again, I'll make up the numbers, but let's say one is a 10J and the other one is 8J. And likewise, it's symmetric, right? So minus 8 and minus 10 J's are here. But it's possible that you may start stable, and some poles may arrive from negative infinity, and they may eventually cross over to the unstable side. There are obviously infinitely many roots when the delay is not 0, so we obviously don't see them in the finite domain because they're at negative infinity with real part. But eventually, as the delay value is cranked up, these poles will start to crawl into the finite domain, and they will start threatening stability by touching the imaginary axis. In the meanwhile, as we increase the delay value, it's possible that this unstable pole will actually make a loop and come back to stable territory. And if none of the other poles eventually, in the meanwhile, do not cross over the imaginary axis, therefore they're already in the stable domain, then we actually achieve a stability reversal. When delay is 0, we start stable. When the delay is a critical value, we are unstable. Onto the next critical value, we're unstable. And then the next critical value, the system will stabilize again. And there are some examples, many examples of this type in the literature. Okay, so now let's go ahead and study a routes array problem. And that will be eventually very relevant to what we want to do. And so this is a case when there are no delays. So this is a standard problem that you can find in many undergraduate controls textbooks. And if you're not familiar with the routes array, obviously you will need to do some little reading on the side. So assuming that you have exposure to this array and how it's constructed. And so we start with our characteristic equation here with F, and we would like to analyze stability with respect to K. Right? So we want to understand stability with respect to the K value. For which K values is the system stable? For which K values is the system going to be unstable? Okay. Of course, there are different ways to analyze this. You can also use root locus to analyze this, but I want to use routes array because there's a purpose for it in the later slides. All right. So this equation, if you organize it, is in this form, and then we can build our routes array as follows. Okay. And so what we would like to do is, using the routes array, we want to investigate stability. And as you will remember, routes array says the number of sign changes in the first column, is equal to the number of unstable poles of the system. Okay, so we know that. That's from the literature. And So now we can investigate if there are any sign changes in the first column. And can the value k cause a sign change? Of course, given the structure of the problem, this minus sign here, right, for some positive k value, right, can cause a sign change in the first column. What do we mean? Well, let's set k equals 10. When k equals 10, the first column is 1, 2, minus 7 over 2, and 11. And now let's count the number of sign changes. 1 to 2, no sign change. 2 to minus sign, 1 sign change. Minus to plus sign, 1 sign change. There are 2 sign changes. Therefore, for k equals 10, the system has 2 unstable poles. Again, it's very easy. You can plug in k equals 10, solve the roots, and you'll find that of those 3 roots, 2 of them have unstable poles. Good. So now, how do we capitalize on this? Well, there's something really important here. What is important is the critical value k star, for which the first column entries are at the transition of changing sign. And that is what we want to investigate. So in other words, when does the row 1 in this case, when does it become 0? And that will become 0 for some critical value k star. And that k star is the boundary, imagine, between stable and unstable behavior. Because if k is less than k star, the system will be stable. If k is greater than k star, the system will be unstable. So we want to find an exact value for the boundary separating stable from unstable behavior of the system in the k parameter space. And that we can easily find. K star equals 3 will separate the system from stable to unstable. So now, as a matter of fact, in this case, it's very easy to demonstrate. You can, if you look at the real and imaginary parts, right, and if you perform a root locus operation here, so you have a pole at -1 and you have 2 complex poles when k is 0. And based on the root locus, we know that these poles will go left and then these poles will go right and cross over. And then there are some asymptotes, right? And we know that there's going to be these poles on the imaginary axis at j omega, right, for some k value, and that k value is actually k star. At the k star value, right, we have j omega value, and that will indicate an instability initiation. And the k star is the separator value. In some sense, we have the function of k. When k is 0, the system is stable. After the k star value, the system remains stable. And then after that, it will be unstable, right? Okay, so the k star is equal to 3. So we know that. That's good. Now the question is, what is omega value? So let's find this omega value. Maybe you can call it omega star to be consistent. So what is omega star value? There are 2 ways to find it. You can either plug in k equals 3 in the Cartesian equation and then solve for s. And then of those that are on the imaginary axis will give you the omega star value. The other one that is actually much more practical is from the routes array rules. You need to check the row 2. When row 1 is 0, it implies that there is a possibility of a j omega root. Okay, and that's the property from routes array. So when row 1 is equal to 0, it is possible, not guaranteed, that there is a pole at s equals j omega. Okay, row 1 is 0, and then there's a possibility of a j omega root. Good. Now, how do you find a j omega? The other alternative way is to use row 2. How do we do that? We take the row 2 elements. In this case, I call it R21 and R22. And if they have a sign agreement, in other words, the multiplication is positive, then omega s equals j omega exists. If this is satisfied, and we can compute omega star value. Good. That's actually what I'm doing here. So it became a little mess, but you can easily confirm that for k equals k star, R21, R22 multiplication is indeed positive. There's a sign agreement between the row 1, row 2 elements. In that case, the omega value will be found by the ratio of R22 to R21 and then square root. So at square root 2, there's going to be a crossing. That's an omega star. So now we find k star equals 3 will yield a crossing at s equals j omega star with omega star value square root of 2. Again, you can confirm this in different ways using root locus or solving directly with the poles. And but this property of Raoult's array is really helpful to identify that crossing value directly from the table instead of going to a higher order polynomial of the characteristic equation. Okay, we're gonna come back to this slide, so just keep that in mind. We're gonna come back to this slide a little later on and use it for a different purpose when there are delays. But what is important is these results will not work if you have delays in the equation. That's easy to show because imagine you have an exponential minus tau s in the equation. This exponential tau s is not compatible with Raoult's array. There's no way you can put this term into the array. You can't do that. As soon as you have a delay problem, Raoult's array is not going to work. All right, let's move on. Now I'd like to discuss a really interesting transformation here called Recasius transformation, attributed to Recasius, who proposed this transformation to investigate the stability of a time delay system. And so let's take a look how this transformation works and where we go from here. Now, the proposition is that this transformation suggests that whenever you see an exponential function in the characteristic equation, you can replace it with this right-hand side term. Okay, how is that possible? And what are the conditions that need to hold for this to be true, right? And of course, we are focused on imaginary axis crossings. We know why at this point. And obviously the proposition is that t is real. It can be positive, it can be 0, it can be negative, and make sure you check the infinite case. When t is 0, the right-hand side is 1. So exponential minus tau s equals 1, and so tau equals 0 case, there's a correspondence between them. So t equals 0 and tau equals 0 are the same thing. So non-delayed system stability. And when t goes to infinity, the right-hand side is minus 1. Right? I'm assuming omega is finite. And in that case, exponential minus tau s becomes minus 1. So what you can do is you can substitute minus 1 in place of exponential functions and check if omega is a solution. S equals j omega is a solution. So that's the infinity case covered. T equals case easily covered because that's the case when the delay is 0. And then we need to investigate separately when the t is positive some value other than 0 and infinity. Actually, because 0 is actually not a positive number. Or whether or not t can actually be negative. Good. Now, t plus minus infinite does the same thing because the right-hand side is always minus 1, whether t is plus or minus infinite. All right, so let's take a look if or under what conditions first this transformation would be useful or would hold rather. And before we do that, we need to note down, and there has been some confusion in the literature or among some colleagues, and thinking that this is actually a Padre approximation. It is not a Padre approximation because first order Padre approximation has tau on both sides, whereas here t and tau are different parameters. We are introducing a new variable t. Some literature called t is a pseudo delay. This is not a Padre approximation. And in a moment, we're going to actually show that it is not an approximation to start with. It is an exact transformation. All right, how do we make it exact? Well, we just play with some complex numbers. The norm on both sides of the equation is equal to 1. You can, with simple math, we can show that. And then we check the phase conditions. The left-hand side has a phase of minus tau omega. The right-hand side has a phase based on some arctangent functions, right? So if you draw a little phasor here, right, with the imaginary part, minus omega t, and real part 1, right? And then you can take the tangent inverse. And likewise, you do the same for denominator. You organize, you get the minus sign out, the minus signs will cancel, and then you end up getting this form. In other words, the recursive transformation is exact as long as this equation is respected. That's how we should see it. Good. All right, what does this mean? It means you are given a Cartesian equation with s and exponential functions. Wherever you use exponential functions, you substitute, you replace them with 1 minus ts, 1 plus ts. And that gives you a new Cartesian equation. Let's call it fr. And you have these denominators, but they will not make problems for you because you can expand the Cartesian equation, whatever power you need here, and to make it a polynomial. It will be a polynomial in s and t is equal to 0. Your goal will be to solve s equals j omega for some t values, t star. And once you find omega star and t star, you substitute them back in here, and then you can recover the tau. Using this arctangent formula, you recover the tau values. And once you have tau and omega, you can actually start analyzing stability. Now here I put a power q here because if you have, say, exponential minus 2 tau s in the Cartesian equation, right, when you do substitution, you're going to get something like 1 plus t s squared. In this case, q equals 2, so you have to expand the equation by 1 plus ts power 2 to cancel this with that. So then you can get a nice clean polynomial parametric in terms of t. Good. Now, a couple of points here. Number one, we said that the system with delay has infinite many roots, infinite many poles. But now we arrive to a polynomial that has a finite power, parametric in t. How come we still have a correspondence in terms of infinite many roots? Well, as a matter of fact, the infinite dimensionality of the problem is not lost, but is actually repackaged in some different form. First of all, indeed, a polynomial with finite power in S will give you a finite number of poles. But don't forget that t is a parameter that is continuous between plus minus infinity. For every t value, you have finite number of poles, but there are infinite many t values that are candidates for this to be 0. Moreover, once we solve the omega and t values, we back substitute them into tau, and we actually reveal the tau values. We will have to have infinite many tau values because the counter L will run between plus minus infinity. Therefore, we'll have infinite many tau values for one crossing, so the infinite dimensionality is not actually lost. Secondly, if you inspect this polynomial, Ps of t, it very much looks like what we just investigated here when there are no delays. It's a polynomial parametric in k in this example, and here we have a polynomial parametric in t. And this was only possible because we used the recursive transformation to convert the system Cartesian equation into a form that is compatible with Raoult's array. Now, what we can do is we can actually study P of S of t for some critical t star values and critical omega star values, just like we have done in the previous slide with the Raoult's array, and then use those omega star and t star values under the arctangent constraint to compute the corresponding tau values. All right, why don't we just demonstrate this over an example? And here's something a little bit more complex than the one I saw earlier, because this is a commensurate degree 2 polynomial. So a simple Euler identity will make this equation very, very messy, and it will be difficult to solve it using Euler's identity. So what we can do is we can substitute the recursive transformation for each of the exponential functions. And then we can expand this equation. We can multiply both sides by 1 plus ts squared on this side too. And this is okay to do because 1 plus ts will never be 0. So we are not introducing any artificial roots here. And if you multiply this whole left-hand side here by 1 plus ts squared, this term will cancel with this one. One of these will cancel, but not both. So we're going to have a multiplier here next to this with 1 plus ts. And of course, this term will get another multiplier. Okay. So now, if you organize it, it's going to look in this form. And s squared plus 2s will get the 1 plus ts squared next to it. The other term will get only one of the 1 plus ts terms because the other one will cancel. And here we have 3 1 minus ts quantity squared is equal to 0. Okay, so now our goal is to take this Rouse array. Right, and that's why I say refer to example on slide 30 that we just covered. And check if there are some t-values for which the first column of the array will change sign. And as I also noted earlier, make sure you check the t equals 0 and infinity cases separately. Okay, and once you do that, you will have obtained all the t values for which a crossing is going to happen or is likely to happen. And then you go to the row 2, you go to row 2 of the routes array and construct a sign agreement condition, as we have done earlier. And if the sign agreement condition also holds, then you know that there's an omega value that you can compute with the formula square root of R22 over R21. And I'm really just repeating what slide 30 has already done. And once you find the omega and t values, you use the arctangent formula to recover the tau values. Are we done? No, we are not really done, but we have actually discovered the tau and omega values that are responsible for possible stability switches. And once we have this information, root sensitivity calculation and tau delayed decomposition tasks follow immediately. Of course, we can't do anything without computing omega and tau, and probably maybe for this reason, there is a lot of focus in the literature in making efforts or revealing ways to efficiently compute omega and tau from the characteristic equation. All right. So now we're actually going to start discussing the CTCR concept. Before I get to that discussion, however, what I would like to do is I would like to go back and review this example with a little bit more detail. And again, in parallel to slide 30. So let's just do that first. Perfect. So in this case, we have found H. Oh, I'm sorry. We have found H, right, which is now a polynomial. H is a polynomial in S and T. And I believe it is, let's actually take a look. It's actually fourth order. Doesn't really matter. It's in fourth order polynomial, right? Bunch of coefficients that are functions of T. The leading power of S power 4 is not affected, is affected, I'm sorry, by the T value too. So we have T squared times S to the 4. That's how it starts. Okay, so in other words, we can imagine, we can actually consider this to be in this form, right? Some coefficient C sub K, a polynomial in T times S power K, right? Sum K from 0 to, let's say, in this case, 4. And therefore, we can build a routes array with row 4, 3, 2, 1, 0. And obviously, the first top 2 rows will be populated by the coefficients, right? So now we have C4, C3, C2, C1, and C0. And we can put a 0 here. And our goal is to follow the standard rules of routes array and populate the remainder values on the routes array. In particular, actually, we will notice that there's actually one term here. There won't be a second term. And this is our R1. Equate that to 0. R11 is only a function of t is equal to 0, so we solve the t values. There may be obviously multiple t values, and these are candidates for causing a crossing. Not all of them may cause a crossing. None of them can cause a crossing. Some of them can cause a crossing. All of them can cause a crossing. We have to check one by one. And what's the condition for crossing? We have R21 times R22 multiplication must be positive for omega to exist. And if this is positive, then omega is equal to R22 over R21 square root. Okay, so for each of these T1s, we go back to the R21, R22 condition. Then we check if this positive condition holds. If it holds, then we compute an omega. So as an example, maybe T1 will cause an omega 1. Maybe T2 won't cause an omega 1 because it doesn't satisfy the inequality constraint here. Maybe T3 will actually cause an omega. And maybe T4 and all the others will not cause a crossing. So then to summarize, we have T1 causing a crossing omega 1, T3 causing a crossing omega 3. Good. So now we can use T1 and omega 1 in the arctangent formula to compute the corresponding tau values. And then we use arctangent formula once more time to compute another set of tau values. This is tau 1, and maybe this is tau 3. Because just to stick with the correct subscripts, right? This tau 1 will have a counter L1. This tau 3 will have a counter L2. So there are infinitely many tau 1 values determined by the counter L1. There are another infinitely many tau 3 values determined by the counter L2. So now we have two sets of infinitely many delay values. Each set of infinitely many delay values causing a crossing at s equals j omega 1 or s equals j omega 3. And now we need to investigate how each crossing is happening across the measure axis, whether in the positive or the negative direction across the measure axis. And then we need to kind of combine all of this into a delay decomposition investigation to study stable and unstable regions along the delay interval. So obviously you can clearly see it becomes very quickly complicated and a little bit more complex when we have multiple crossings, and each crossing will correspond to infinite delay values. And now this is very messy problem with multiple sets of infinite delay values corresponding to crossings over the measure axis. Now, how do we keep track of the movement of all these eigenvalues of poles over the imagine axis to be able to come up with a reliable way to decompose the delay axis as stable and unstable behavior? That's the question. Now, a cluster treatment of Kratis roots was exactly motivated by that observation, and I will explain it over the arctangent formula, and that's how the CTCR concept has been revealed. And nevertheless, we don't need this equation to explain the concepts, as the concepts hold irrespective of the recursive transformation. And first of all, since the routes array is finite dimensional in terms of the number of rows, right, and it will be finite dimensional because there are only a finite number of solutions, right? These are just polynomials. R11 is a polynomial. T has a finite power. The candidate solutions are finite dimensional, and only a finite number of them exist. And the number of crossings will also be finite. All right. So that is really important. So there are only a finite number of possible locations across the measure axis through which the system eigenvalues can migrate, and whether to the left or to the right. Okay. And for each crossing, and I also highlighted this in the previous slide, for each crossing, there are infinite many delay values. For example, if there are two different crossings, as in the previous example I showed, then we have two infinite many delay values for which a respective one of the crossings happen. We have two sets of infinite many delay sets. We have two sets of infinite many delay values, sorry, and each set corresponding to a particular crossing. Okay, so let's just, carefully observe and let this sink in. All right, so now we have a crossing at s equals j omega 1. And of course, this corresponds to some t value, t1, for if you're using recursive substitution. You don't have to. And for this crossing will happen at infinite many delay values, as we are showing along this axis here. If you have two crossings, then you have another crossing at s equals j omega 2. And if you're using recursive substitution, again, you don't have to. You have a value t2. And if you're using recursive substitution, omega 1 and t1 are using the arctangent formula to compute these delay values here. Likewise, if you're using recursive substitution, you use omega 2 and t2 in the arctangent formula to compute another set of infinite many delay values that are shown here at the bottom. Okay. Of course, if you have more than two crossings, then the story continues. You just keep, ideally, you can just put them on top of each other. You can stack them for a clear view of what's happening. Second of all, observe that for a given field frequency, omega crossing, the delay values are 2 pi over omega apart from each other. So for a given frequency, delay values are periodic, 2 pi over omega. Okay, they're periodic within their own set. If you go to the next set, the periodicity property changes, or the periodicity property holds, but the length of the period changes because omega 2 value is very likely different than omega 1 value. Okay, so if omega 2, for example, is a smaller value, then the periodicity will be larger, so that the gap, the frequency at which these delay values dictate a crossing across the imaginary axis will be less. So just to recap, if omega 1 is small, then this periodicity will be small, meaning the crossings at j omega 1 will happen with delay values that are very densely packed because the distance between them is small. So it means it's like very quickly a clock clicking. There's going to be crossings over the imaginary axis back and forth, back to back as the delay values increased from 0 to a certain value. The appearance of these omega 1s will be very frequent because the delay values are spaced with small distances from each other because omega 1 is large. Whereas if omega 2 is small, right, the delay values for which the crossing omega 2 will happen, they are very scarce and they're not very densely packed. So there's going to be a one click, and next time a click happens, so much delay has to be increased to that value before the next crossing happens. Okay, so you can think of it like this. All right, so now considering all these important properties, now let's think about, all right, how can we actually bring an organization to our understanding of stability analysis as a process. What is important is whether or not you have two or more crossings, right? What is important is there is only one delay axis that we are actually concerned about. Okay, these multiple delay axes that we are drawing here, they are useful for visualization and explanation purposes, but we actually have only one axis that we need to worry about. And so that's the delay axis. That's the problem that we are trying to solve for a delay tau. And of course, delay equals 0 is our origin, right? And what we need to do is we need to actually project all these delay values from each of these axes onto our actual delay line in green. So if blue, let's say delay values are happening more frequently, right? And when you drop them over delay axis, right? The blues will appear more frequently than the others. Whereas if the red are happening less often, right? Because their periodicity is large, because their omega-2 is small, right? Then again, they will be dropped onto this axis, and they will obviously appear less frequently than the blue ones. So now, if you look from left to right, as delay is increased, the blue, the delay values associated with the blue will actually click, so to speak, on delay axis more often than the delay values that arrive from the red crossing associated with omega-2, because their periodicity is much larger. Okay, and that's really important because as we imagine how the crossings happen across the measure axis, where the delay is from, as we increase delay value from 0 upwards, right? And which crossing will happen depends on what is the next delay value that we expect for which the crossing will happen. So when delay is 0, let's say the system is stable, and as we increase delay value, we're going to hit the first critical delay value, which means we're expecting a crossing at the blue one at omega-1. We increase delay value more, and now we touch this critical value, but the triangle comes from the red set, so we expect a crossing at omega-2. We increase delay value more, the next one is from blue, so it's a crossing at omega-1. We increase delay value more, another crossing omega-1, right? Another crossing at omega-1. Increase delay value more, a crossing omega-2, another crossing omega-1. So you see that the periodicity property along the actual tau axis, there is no periodicity of crossings, because crossings arrive from different crossing values, and each crossing value arrives from different delay values that have their own periodicity. So when you drop all these numbers onto the single tau axis, there is no periodicity left between subsequent delay values, because those delay values do not necessarily come from the same set. And actually, that's really important property to know. But individually, right, triangles are periodic with respect to each other, and the red dots are periodic with respect to each other. That obviously we know from the structure of the problem now. Now, this is where actually the CTCR kicks in, because in some sense what we're saying is there are what we call root clusters. And there are infinite many delay values, tau 1L, for which a cluster of roots across the measure axis are determined. And there is another set of delay values, infinite many, that determine another set of root clusters that are responsible to cross the measure axis at j omega-2. So each root cluster, right, is associated with a frequency, and across that frequency at j omega frequency, at infinite many poles or roots will cross. And for the delay values, for infinite many delay values, that are periodically spaced. So now, in some sense, on the complex plane, we have these, you can also use color coding, right? We have a root cluster in red, right? And when we hit that the particle delay value in triangles, a pair of poles will touch the measure axis. There is another root cluster in blue. When the delay value hits the blue delay values, a pair of those roots from that cluster will touch the measure axis at j omega-1. Okay, and the appearance of these crossings in the actual delay axis is determined by projecting all the delay values onto the same axis and accounting the crossing directions. Then, whether stabilizing or destabilizing, right, as the delay values increase from 0 up to some upper bound. All right. So the first, and actually I just discussed this, the first proposition of the CTCR is that there are only a finite number of crossings, and each crossing is determined by an infinite many delay values, and when a crossing happens for all the roots that actually create the same crossing for these, the infinite many delay values are called a cluster, and there are obviously k number of clusters because each cluster is associated with an image axis crossing, and there are k image axis crossings, so there's got to be a k number of clusters. And of course, each cluster is associated with its own frequency, and it has its own period for each occurrence of delay values within its own set. Second proposition is associated with the invariance property of the crossings within a set. It says that when a crossing happens, let's say in a destabilizing direction in the blue set, then we know that in this blue set, all the other crossings will also be in the destabilizing direction for all the delay values in that set. In other words, if you have only one piece of information about the crossing direction, that information is automatically applied to all the other delay values in that set without having to compute the crossing direction for each of the elements in that set. Likewise, if the crossing direction is, let's say, stabilizing in the red set for one data point, all the data points for delay values in that red set will also be in stabilizing direction. And there's no need for us to compute the sensitivity function for each of the triangles separately, because one piece of information automatically applies to all the other delay values in that particular set. So now this brings a simplification and a schematic way of looking at how crossings arise, how delays determine crossings, and how these crossings favor stabilizing or destabilizing behavior. So, as an example, maybe let's take a similar example, right? We have two crossings, so we have a blue and a red set, each corresponding to infinite many delay values, and then each has infinite many delay values, and in each set, these delay values will create a crossing at omega 1 or omega 2. And imagine that the blue set is a destabilizing set because it's positive, so the crossing is from left to right. And it's sufficient to compute this from only the first delay value, or one of the delay values is enough. And if you know that this one is destabilizing the crossing for this delay value, all the others will be destabilizing. Therefore, I put the counter L here. So no matter what L is, the crossing is destabilizing this cluster. And imagine, for an example, the second set is actually a stabilizing set. So again, you can just use one data point to compute the stabilizing direction. And then if it's stabilizing, all the others will be stabilizing. And that's what the proposition 2 says. And therefore, there's a counter L here. And as a matter of fact, maybe this counter should be L1 and this counter should be L2 because they don't have to be the same count. They don't have to be the same counters. And for that reason, all the delay values in the red set will be stabilizing and signified by the negative sign. Okay, next we project all delay values from each of these sets onto our main delay line. Right, maybe I should use again triangles here for the red and dots for the blue set, and we have this. Now remember, this is a destabilizing crossing, this is stabilizing crossing, this is destabilizing, destabilizing, stabilizing, destabilizing, stabilizing. Right? Okay, so those attributes come along with the delay values. And this is destabilizing crossing, and that's a stabilizing crossing, etc. And you have many of these. And of course, when the delay is 0, you know if your system is stable or unstable, right? Because that's easy to analyze. Let's say your system is stable for delay 0. Okay, the system is stable for 0 delay. And up to the next delay value that will destabilize the system will remain stable because we have a retarded system. So stable, 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 stable. Here it's always stable. And then when we hit the blue value for delay value at blue, right, which is this value here at tau 1, there's a crossing at omega 1, and it's destabilizing. So now we have two unstable poles. So after this crossing happens, the system has two unstable poles. Good. And now imagine now you increase the delay value further, you're still unstable, 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 unstable. You hit this red value, and the red value is actually stabilizing, and it comes from the red set. Okay, it means those two unstable poles must return to stability. There is no other way because there are no more than two unstable poles. If this crossing is stabilizing, those two unstable poles must return back to the left-hand side of the complex plane. Now you're back to stable, 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 stable. You hit the next delay value, it comes in blue set, it's destabilizing, so you have two unstable poles. So if you actually were to draw a mini complex plane here, real and imaginary, right, you start stable, as an example, maybe you start stable with two complex poles, and as you increase delay value, the delay value is 0 plus, right? You have infinite many poles. And we don't know which pair, but a pair will cross over. Maybe these two, maybe the other two from the negative infinity, they will cross and destabilize the system at omega 1 crossing. And then they will then turn back and stabilize the system at the crossing omega 2 and with a stabilizing direction. This is an example where one would actually see these stability reversals, and where you can actually really show that this system can become stable for larger delays, and it can be unstable for smaller delays. It's always stable connected to the zero delay origin. That's actually no surprise, because when the system is stable for zero delay, you expect it to remain stable for some margin of delay. But what is really interesting is once it becomes unstable, it can actually come back to stability. All right. So just to continue again, to give you some form of familiarity, the smallest positive delay value in each cluster. So here in this case, this one is this one. And in the red set, the smallest positive is this one. Those are called kernels. Now, what is nice about this is that since if you know the kernel value, tau 1, and because we know the frequency omega 1, we can generate the other delay values by the periodicity property 2 pi over omega 1. Likewise, in the other set, we can generate the other delay values by the periodicity property 2 pi over omega 2. In some sense, the knowledge of omega 1, tau 1, and the crossing direction, right, destabilizing, and then omega 2, tau 1, and crossing direction negative because stabilizing, is sufficient to complete the entire stability analysis. What would you do? Well, first of all, use omega 1 and tau 1 to complete the crossing direction. You find it to be positive, and it's automatically applied to all delay values in that set. No need to recalculate it. And then knowing omega 1 and tau 1 using the periodicity property, you can generate all delay values in the blue set. And repeat the same thing for the red set. And then you drop all delay values in the tau axis, and you can do an accounting for stable and unstable. Perfect. So let's go back and look at that example again, or something similar actually, because this is commensurate degree 1. And before we end, now we can actually approach this using recursive substitution, although there are other ways to solve the crossings. And the idea is very similar to what we have done before. And then I'll show you a maple file in a moment where I actually do the computations. And then we'll find that actually the system is indeed two stable regions between 0 to 0.105, another stable region from 0.866 to 1.28. Let me just switch the screen, and I'll share with you the maple file in a moment. Perfect. So here's the maple file. I actually have a PDF version of this. And I have the original code if anyone wants to see it. It was just easier to kind of show this on a PDF file. So here's the starting point, the characteristic equation. And then I obtain the precocious transformation version of the characteristic equation. And I reorganize it so I can clearly see this in S-cube polynomial. And then I assign coefficient C0, C1, C2, C3 as a coefficient of S. And these are the coefficients that I use to produce a routes array. And in this case, it's very simple to create a routes array elements. This alpha is actually the R11 term. And so what I do is I equate this to 0 and solve the roots. And I find two roots. These are candidate T1 and T2 solutions. Then I go and check the sign, then I assign T1 as 0.05 here, and then I assign T2 as 1.845. And for each of these T1 and T2, then I have to check the sign condition if the R21 and R22 have consistent sign. And so what I do is I check the R22 and R21. They are both positive, so they have a sign agreement. And I then check for T1, and I do the same for T2. R21 and R22 have, again, sign consistency. It means that omega exists for each pair, each one of the T1 and T2 values. So for T1 value, I compute the omega value, which is square root of R22 over R21. I only work with positive omega values. It's easier. And then for T2 value, I also compute omega value using square root of R22, R21. I find two omega values. And remember now we have a T1 value, 0.05, corresponding to an omega 1 value 533. So I use that omega 1 and T1 in the arctangent formula to calculate the delay value, tau 1. And then I calculate then the tau 2 values using T2 and omega 2 using the arctangent function, here 0.86. Of course, these are not the only delay values because these are actually the kernels. And I actually check them because if I add another pi or if I subtract another pi, they will become either negative or they become much larger than these values. So these are the minimum positive values. So these are the kernels. And if you have the kernels, you can use the kernels to calculate the sensitivity. And you find that the first kernel is destabilizing, real part is positive. The second kernel is stabilizing, real part is negative. And so now we have a good story to tell. The system is stable when the delay is 0. We know that. You can easily actually confirm from here when delay is 0, the system is stable. And then as we increase delay value, the first crossing will happen at this value because this is smaller than the other one. And then we need to check how often this appears. It has a periodicity. It will appear more frequently because it has a larger frequency. And this one will appear with less periodicity, less often because it has a larger periodicity because it has a smaller frequency. And then we have to put all of these on a delay axis. And that's actually what I'm doing here. If you take a look, I carry those numbers from Maple file 0.005, and then 0.105 will repeat next time at 1.28. It will repeat again at 2.46, etc. And whereas 0.866 is the smallest positive for the red set, and it will repeat again next time at 2.801. It actually has a much larger periodicity, as I said, because it has a smaller frequency, whereas the blues will repeat more often. So the destabilizing behavior happens to be more often than the stabilizing behavior. But it turns out that these blue and red markers are arranged in such a way that the numerical values are arranged in such a way that we actually have two stable pockets here, or intervals. So we start stable when the delay is 0. As we increase delay value, we have a crossing blue destabilizing, so we have two unstable poles here in the next segment. But then the next one we hit is a red one stabilizing, so those unstable poles will become to the stable territory, and now we are stable again. And then as a crossing, we have become unstable, two unstable poles, onto unstable, onto the next one, another two unstable. So we have two more, 4 unstable poles. And then this is stabilizing. So if you go to the right-hand side, we have 2 unstable poles. So you can see that eventually unstable poles will prevail because the blues actually happen more often than the red ones. Eventually, the right-hand side will be busy with a lot of unstable poles. All right, I'm going to stop here, and we're going to continue with section 3 later on. Thank you so much for your time. Again, if you have questions, just drop me a line. Really appreciate it. Thank you. Bye-bye.